Okay, Lab 5. Subject matter is Newton's laws. There are 4 activities based on these 4 Bizlets. Here are the questions that we're trying to answer. And here is problem 4.2, which is the item that we're using in the first problem. This one happens to be static. Most of these are activities. So you can read the instructions, and we want to get the components of the vectors, and we can do that from the grid, although in some cases the arrows don't terminate at an intersection of lines, so you have to read between the lines to get the components. And you might notice we have a 20,000 kilogram plane, so that would be 200,000 newtons, right? If we multiply by g is 10, it's about 200,000 newtons, and each box is 40,000 newtons, so we go 1, 2, 3, 4, 5. Okay, there's the 200,000 newtons. Okay, so the thing seems to be legitimate. And so in the questions that I minimized over here, you can get the components of all the vectors, add them all together, and see what the net force is. And then once you know the net force, you can make some statements about the motion of the airplane. Okay, here's problem 4.3, the next question. If we go into Moodle and we scroll down, whoops, anyway, that writing is there, we can see the questions for this simulation. So we want to go to the simulation and find the acceleration of the cart, the applied force. We want to see if it's consistent with Newton's second law, and then we want to pick out amongst all those statements which ones are true and correct. So let's go to the simulation and begin to do that. Before we play it, let's familiarize ourselves with the situation. We have a 100 kilogram wagon, a 20 kilogram block on a frictionless bed. The block is on a frictionless bed. It is pulled with a constant force, so the force is constant. We can measure positions in meters. The time is given with the clock in seconds. And so we want to collect some data and see if it behaves according to Newton's second law. Okay, you're learning about Newton's second law, but here's a good question. What's going to happen when the animation starts? What are you going to see? Just try to picture it in your mind and see if you're surprised or see if you guess what's actually going to happen. How well do you understand Newton's laws of motion at this point? Okay. Looks like it starts from rest. What's the green block? It's not moving. How come? Okay, so there's what happens. Did you guess what was going to happen? Okay, let's play it again. Watch it one more time. Green block doesn't move. The cart moves. The green block stays stationary. Now they both move. All right. So it's worth thinking this through. So the green block is on a frictionless bed, right? So it has inertia. So to move forward, there has to be a force. And in a regular cart, the force of friction would be there, but there's no friction. So the block stays stationary. There's no force on the block until what? Until the back barrier of the cart hits it. So what happens? What do you think is going to happen in the first part of the motion when the block isn't moving, and in the second part of the motion? Can you guess? Well, since in the second part of the motion there's more mass, the force is constant, what should happen to the acceleration? The acceleration should be higher in the beginning and lower at the end, right? If we increase the mass, then the acceleration should decrease if the force is constant, and the force is constant. We say the sum of the forces, but there's really only one force, and because of the wheels we can assume that this is relatively frictionless as well. So we know the mass, but we don't know the force or the acceleration, but we can measure the acceleration and thus we can get the force. And if the force accelerating the first part, once we know that, we can predict what the second acceleration would be because of the change in mass. Do you follow that? Go ahead, start the calculations as to what the actually what we need to do is measure the acceleration in both parts. So do both parts and measure the acceleration, and notice you have velocity, you have time, and you have position measurements. So it should be fairly easy to get the acceleration through the first half and the second half. And so, since we have the velocities, since we can get the velocities, we can simply get the acceleration this way. So go ahead, I'm going to let you do that, and you can do it over several intervals to make sure. Do it at least twice in each section, and see that you get a consistent acceleration for the first half and the second half, and see what that is. So let's start at 0 velocity and 0 time, and let's go for 4 seconds. Whoops, step back. 4 seconds, a velocity of 2. So, whoops. So 2 meters per second minus 0 meters per second divided by 4 seconds, 0.5 meters per second squared, right, if I put all the units in. So I just ran it for another time interval. You see there's 2 seconds and 1 meter per second, so I'm going to get the same value. Good, so we have a consistent value there. Now let's do the second half. So you might notice that it hits the barrier at, well, 5.7, about 5.7 seconds. So let's move it up to 6 seconds, and then we see it's 3 meters per second. So now let's move it forward 1 more second, from 6 to 7. And it went from 3 to 3.5, so that's advanced 0.5 meters per second in 1 second. Oh, it looks like the same acceleration. It looks like it didn't slow down. The force is constant, so that acceleration can't be correct, right? What should the acceleration be? So did you get this? The net force is just the single applied force equals the mass times acceleration, and the mass in the first part is just 100 kilograms times the 0.5 meters per second. We end up getting that the applied force is 50 newtons. Now remember, this is constant, so the 50 newtons goes here. We have a new mass, 120 kilograms. The acceleration in the second part should drop to that amount. Okay, ready for the third problem. So here's problem 4.9. There are 6 animations. You might run them. Whoops. They all start like that, I think. So take a look at those 6 animations, and then look at the questions that you have to answer. And here's the set of questions for this exercise. Okay, so there they are. you have them on your computer, but just in case someone's watching the video and they don't have the questions, there they are. Take a look at them. And let's go. So run through the 6 animations, and then we'll come back and discuss each one of them. Before you begin, check out the details, right? So it's a 10 kilogram mass, a massless string, so the string doesn't have any negligible mass, and a massless pulley. Okay, so the pulley, if it had mass, would change things, right? But it's just, the pulley's just a massless, frictionless pulley, and so all it does is change the direction of the string. So we can ignore that. All right, let's play the first animation. Notice that its V is -2 meters per second before it starts, right? So it's not moving. Why? Only because the video isn't running. So you got to be careful. It's not starting from rest. And when I play it, whoops. When I play it, what do we see? It just continues at a constant speed going down. Okay, so if you draw a free body diagram, yes, free body diagram, very important, of the block, then there's a tension force going up, Ft, and the force of gravity going down, Fg, and Fg is going to be, if we use 9.8, 98 newtons, and so Ft has to be what? 98 newtons, because sum of the forces in the y direction equals may, but ay equals 0, so it has to be 0. So the two forces have to be equal and opposite. And so the tension in the string, or the tension, or the force with which the hand is exerting on the string, has to be 98 newtons. Okay, animation 2. Animation 2. Play that. And now it's a +2 meters per second. So what changed? Well, it's going up. Does that matter? You might think so, but it doesn't, right? The sum of the forces still have to be 0. The tension force and the gravity force have to be equal. A little bit it defies your intuition, right? Partly because you're imagining that there might be some friction in this, or partly because you're imagining there might be mass in this. But no, it doesn't take any more force to pull the thing up at a constant speed, or let it go down at a constant speed, or if I jump ahead to animation 5, it doesn't move. So, contrary to what you might think at first, these are all equivalent. They're all situations where the sum of the force in the y direction is 0, and the up force, the tension in the string, has to be equal to the down force, the force of gravity, which of course, right, we're just learning this week, is mg, the mass times g. Okay, let's look at animation 3. And play that. Okay, now it's going down with an acceleration. And animation 4, guess what it's going to do? You can probably guess. Oh, it goes up with an acceleration. So now the sum of the forces are not 0. And so the way we're going to get this is, right, let's take the one where it's accelerating up. Ft minus FG, which is negative, has to equal MAY. Right, this is the sum of the forces in the y direction, or that. They have to be equal to the mass times the acceleration in the y direction. And so the Ft, in this case, is going to be MAY, you got to measure it, plus FG, right? It's going to be bigger than FG. So if it's accelerating up, it makes sense the tension force has to be bigger than Fg by what? By the amount of the acceleration. So the acceleration should be easy to measure. Oops. Starts at a velocity of 0. Let's play it. Play it out 1 second. So it went from 0 to 4 meters per second in 1 second. So that's a delta V, right? 4 meters per second minus 0 meters per second over 1 second, so 4 meters per second squared. And if the acceleration is consistent, if we play it out for 2 seconds, after 2 seconds it's 8 meters per second, so we get the same acceleration. So the acceleration is in fact constant, and it's 4 meters per second squared. And going to animation 3, I jumped ahead. You can see after 1 second, it's a negative 4 meters per second squared. And so we get the same acceleration, only negative. And once again, being careful, I ran it for 2 seconds and got negative 8. Good. But now the acceleration term, is negative. And so you're going to be subtracting it from the Fg. And that makes sense because if it is accelerating down, then the up force can be smaller than the down force. In other words, there's a net force down that causes the down acceleration. That means the Ft has to be smaller than Fg. So you're not just doing the calculations, you're keeping the physics all in mind. Okay, last problem, 411. Let's see what the questions are for this one. There we go. So if you don't have that on your computer, or you want to know what the questions that we have to answer are, we need the acceleration of the cart, the tension force on the cart, what is the tension force on the hanging mass, the acceleration of the hanging mass, and what is the mass of the hanging object. Those are the questions we want to answer. So, of course, read the instructions. We have a 1 kilogram cart, low friction track, so we're ignoring friction. Connected to string and hanging object, neglect any effects of the pulley. So the pulley is small and frictionless. All it does is change the direction of the string. So the key there, that if you don't know it already, you need to know, is that the tension isn't going to change. So the tension we find here will be the tension here because the pulley is having no effect. The only way it would have an effect is if it weren't frictionless or if it were big and massive. We often do this in lab, but we don't get to do the labs. So here we are in the simulations. Oh yes, one more thing. Notice that the direction x for the cart is this way, and the direction x for the hanging mass is down. So this is a trick that's often used because the string is changing the direction of the force. And so this will have a positive acceleration. We want this to have a positive acceleration as well. So it's just convenient to switch the coordinates so that both objects are moving in the positive x direction, because remember, the velocity of these two objects and their acceleration is going to be the same because they're tied together. Okay, so any force problem begins with the diagram, which we have, and step 2, always draw a free body diagram. So draw a free body diagram, it's good practice. Draw a free body diagram of the cart. Pause the video, draw the diagram, and then come back. There it is, and even though we don't need the normal force, the Fn, or the gravity force, the Fg, mg, because we're not concerned about what happens along the y-axis, only along x. So, but the correct free body diagram has 3 forces. They're not balanced. The cart is going to accelerate. And so we now use some of the forces in the x direction to get the tension force. So write that out. And so since there's only, we write sum of the forces equals max. The only force in the x direction is the Ft. That's equal to max. And so we simply get the tension force by multiplying the mass times the acceleration. So you do have to measure the acceleration. But notice when you play the simulation, the velocity versus time graph will be plotted. And so for acceleration, you're going to use, and you'll see that it's a straight line. And so the slope of that line, or the change in velocity over change in time, is the acceleration. Let's just play it and see. Yeah, it starts at 0. The velocity changes consistently in time, and so it should be very easy to get the acceleration. And from the fact it's a straight line, you can say what? The acceleration is constant. The slope of the line is constant. Delta V, delta T. Okay, now that you have the acceleration, you can calculate the force. And now that you have the force, the tension force in the string here, you have the tension force in the string here. So now we can get, and they have the same acceleration, right? So now we can get the mass of this object. How? Remember, diagram, free body diagram, sum of the forces. So draw the free body diagram and use Newton's second law equation, sum of the forces along x equals max, to solve for the mass of the object. So do that before you watch me do it. So this is what you should have done, and if you're unable to do it, you really need to learn how to do it. So right, we're going to use, remember, we're labeling down as x. So we're doing sum of the forces in the x direction equal max for that hanging mass. So to sum up the forces in the x direction acting on the hanging mass, that's why we draw the free body diagram. So there's the free body. I don't show the rope, I only show the forces. So the rope, the string, pulls up. That we call the tension force. And the force of gravity, or the earth acting on the mass, acts down. We call that the force of gravity. And that's equal to mg. And I drew them like they're equal, but they're not equal. This one has to be bigger. You should recognize that. It has to be bigger. Why? Because it's accelerating in that direction. Okay, now you have the 2 forces, so you can sum them. Remember, down is positive. Notice, this is our x direction. That's a little unusual, but that's what we're doing. So the mg force, the force of gravity, is positive. The Ft force has to be negative. And the acceleration is positive, so that's max. And notice the mass, that's the mass here and the mass here, that's the mass of the block. So we've got to do some algebra. So if I add Ft to both sides, this becomes 0. And if I subtract max from both sides, I get mg minus max equals a positive over here, Ft. And then I factor out m. and I end up with the equation. I'm going to go up here. You end up with the equation, and you really should make sure you can do this on your own because you'll need to do it on the quiz. G, I'm skipping a step of algebra, but G minus AX. And so now put in the number for FT, put in the number for G, put in the number for AX with the units, and you will in fact get the mass of the hanging mass, and that's what you want. I'm not going to do the numbers for you. I'm going to let you do that. And finally, the table of contents. So if you're looking for a specific problem, you can find it without having to scroll through the entire video. Good luck.